Okay, so let's take a look at the next one. So this one's a little bit more complicated. The question, the form I have says, a string under a tension of 48 newtons is used to whirl a rock in a horizontal circle of radius 2.2 meters at a speed of 20.05 meters per second. The string is pulled in and the speed of the rock increases. When the string is 0.548 meters long and the speed of the rock is 57 meters per second, the string breaks. What is the breaking strength of the string? Answer in units of newtons. In short, they're looking for us to find the breaking point of the string. We can only put so much force on an object before it breaks. So, if I were dealing with a person swinging a rock, but I do this in a slightly better drawing. Stretch Armstrong here is swinging a rock in a circle. Imagine it's coming out of the board, going in this side, coming back around like that. At this point here, with our rock, we could draw a free body diagram that looks like this. Let me see. Horizontal circle. Okay, so we've got a horizontal circle. Radius 2.2, the string is pulled in. I will tell you this, the other one that had the plane, I think is a much better description on this. This one's telling us that we have a horizontal circle, which means our force of tension is off this way. In real life, this would actually be angled up slightly so that we could beat out the force of gravity. I want you to imagine that we're actually countering that out, and we're not having to worry about gravity on this one. I will mark it on any problem in the classroom that you would do that type of approximation on it. I'm pretty certain that's how they go through and solve this one. Technically, there is a force of gravity, and we would need something that would balance that out. You can imagine this a lot like the airplane from one of the previous questions, because it had a lift force that actually balanced that out. Okay. In short, we know that our sum of forces in the x at least, there's some stuff going on in the y, but we're actually going to ignore it because we're only looking for the forces in the x direction. We need our tension force to be equal to our centripetal force. It's the force that's actually pulling the rock in a circle. So Ft is going to be equal to mv squared over r. Now they want us to find the breaking point tension, so we would need the mass times the speed squared divided by the radius of that circle. Now we know at the breaking point, pardon me, the breaking point, r is about half a meter, and the speed is 57 meters per second. So we know these two. Our problem is we do not know the mass, so we cannot solve for the breaking point right away. We're going to need to take a look at a different point, something we know a little bit more about. We know at the very beginning that we have a force of tension in the wire of 48 newtons, and that when we do that, it is moving in a circle. In fact, the free body diagram that I drew can still be applied in the very first part too. We know that 48 newtons is going to be equal to mv squared over r for the very beginning, just like it is at the end. But at the beginning, we have different values. We have that it has a radius of 2.2 meters and a speed of 20.05 meters per second quantity squared. 20.05 squared divided by 2.2. This gives me the following. 48 newtons equals whatever the mass of this rock is times 182.7. What's that going to be? Meters per second squared. I can now divide both sides by that. You can also multiply by 2.2 and then divide by 20.05 squared. You should end up with the same thing, but we're going to find that the mass is equal to 48 divided by answer equals something like 0.2627 kilograms. On this one, because they gave me a number with 4 significant figures, I'm going to kind of keep that for now. I know we're not following the exact rules of significant figures, but we know that sometimes we run into weird issues with the online homework system, so I'm going to go ahead and keep that. It's entirely possible that the better way of looking at this would be 2.200, but again, in class, 3 significant figures is perfectly fine. I'm going to keep 1 extra just as a safety. Now we've found the mass from the first one, and we can plug that back in with the other information at the end. So we know the force of tension when it breaks needs to be my mass, 0.2627 kilograms, times, they said that the speed it was going when it broke was 57 meters per second, quantity squared, divided by the radius that it broke at, which is 0.548 meters. Sooner or later I'm going to get used to that. 0.5548 meters. Okay, so I'm going to do 57 squared times 0.2627 divided by 0.548. My force of tension with my calculations comes up to 1,558 newtons. I probably call that 1,560. Let's see what they come up with. They came up with 1,557.4, so we are definitely within 1% on that. All of these would have been acceptable answers. I will comment on this temporarily. We've had problems, and I've even made ones like it before, where we tell you that it's a horizontal circle to try and keep things simple, where you only have to find it here in the x direction. In reality, what you actually end up with when you swing these around is they're down slightly at an angle. In this angle, you would then end up with the following free body diagram. You are welcome to ignore this. I will not ask this type of question in Gen Physics. If you are any of my AP students, you might have concern on this. We have a force of gravity downward, and in reality, when you are swinging this around, you end up with something like this. Here's your force of tension, and there's some angle here, theta. You end up with an x component of your tension, and you end up with a y component of your force of tension. Now, you can go through and you can solve these. When you do your sum of forces in the y direction, you'll end up with, since this is moving in a horizontal circle, I'm actually pulling it here. This is moving in a horizontal circle. This is also theta. You would do the following. Sum of forces in the y equals Fty. I apologize, that's Fty. This is Ftx, and here's the total Ft. Minus Fg equals May, and if it's a horizontal circle, then it's not going up or down. We find that Fty, the y component, must be equal to the force of gravity. Once again, not a Newton's third law pair, it is simply because the forces are balanced there. For Gen Physics, what we're doing is we're ignoring these values here and just going with a makeshift force of tension in the x. This would actually be the real world applications of it, but we are fine looking at it like this. It's a good approximation. All right.